In the previous lecture, we defined this bipartite graph, and we're going to see additional uses of it in this lecture. A first result that is of interest and has to do with the basic exchange property is this idea of local optimality implying global optimality. If you have, let me write it down. So M is our matroid, and for this property, we're going to take a weight function W. So it's some arbitrary weight function. Now, in past lectures, we've seen various ways that we could think about finding a maximum weight base. We could use a greedy algorithm, or we could solve a linear program over the polytope. This is a characterization of a maximum weight base in terms of a local optimality condition. Basically saying if there's no single element that you can swap in order to make your life better, then you must be at a globally optimal solution. So in other words, this is the following. If B and I is a base, it is max weight with respect to this arbitrary weight function W, if and only if the weight of any base B dash is less than W of B for any base B dash that differs from B by one element. So obviously one direction is clear. If it's max weight, then W of B dash is less than W of B for any base, full stop. So what's interesting is to show this other direction. This is really just a consequence of that very first theorem. We're not going to be using the graph from the previous lecture. This is just using the exchange theorem. So suppose that the conclusion is not correct. So suppose there exists some B dash with bigger weight. Well, then we're going to show that we can find some base that differs by just one element that has a bigger weight than W of B, and therefore the assumption of the theorem doesn't hold. So we know that there exists. I'm sorry. We will be using this the directed graph that we talked about in the previous lecture. So there exists a perfect matching. We'll call it again N of the symmetric difference. That's what our previous result stated. What the corollary stated. And you can see how this is gonna work. So since the weight of B dash is bigger than the weight of B, and since the elements that are in B, the symmetric elements, since the elements that are in B and not in B dash are matched one-to-one with the elements that are in B dash but not in B with edges, which means that each one of those could be interchanged, it has to be that one of those elements that's matched up, one of the elements in B dash has a higher weight than the element to which it is matched in B. So in other words, since the weights in B dash are bigger than the weights in B, there has to exist some edge YZ in N with the weight of Z being bigger than the weight of Y. And this is our contradiction of the assumption of the theorem, because this in turn implies that the definition of the edge says that B minus Y plus Z also has to be an independent set. It has the same size as B, therefore it's a base. So it's a base, and it has weight that is strictly bigger than B, while they have difference only one. So this concludes the theorem. And again, it's a simple but very useful application of the last corollary on in the previous lecture that tells us about this existence of a matching. Okay, now let's turn to other uses of this bipartite graph. Again, let M be our matroid. And now let's take two subsets that are the same size, and I, but not necessarily J, is an independent set. If there is a unique, and uniqueness is important here, perfect matching on the symmetric difference between I and J, then this guarantees that J is also an independent set. So this theorem says the following: if this bipartite graph, directed bipartite graph with arcs A of I, contains a unique perfect matching, let's call it N, on the symmetric difference between I and J, then J is also independent. Okay, so again, our picture here is this is I. This is everything that is in E, not in I. And let's suppose that this is J. And the theorem assumption says that there is a unique perfect matching. So in other words, Y1 and Y2 are matched to Z1 and Z2, but there is not an edge from Y1 to Z2 and Y2 to Z1. Perhaps there's an edge perhaps there's one of those two edges, but not both, because then there would be a second perfect matching, and that would violate the assumptions of this result. And again, just to recall that what is the meaning of an edge? An edge between Y and Z means that I minus Y plus Z is an independent set. So in other words, these edges in this picture mean that I minus Y1 plus Z1 is an independent set, and I minus Y2 plus Z2 is an independent set. But just to appreciate what we're trying to show in this result, we actually want to show that I minus Y1 minus Y2 plus Z1 plus Z2, because that's exactly J, is an independent set. So you see that it's actually not immediately obvious from the exchange theorem perspective that this needs to hold. So the edges tell us that one swap is fine, any individual swap, but this graph would be a different graph if I wanted to form the graph, say, on this independent set. Well, then it has different edges. So this theorem is asserting that I can do all of these swaps, not just one of them. So previously, and the graph itself is saying that any one swap is guaranteed to land you again in an independent set. This is saying that you can simultaneously do all of the swaps as long as we have a unique perfect matching. So again, there's something non-trivial happening here. So let's turn to the proof and see how it goes, and also to see where the uniqueness of the perfect matching comes in. Why that is important. So again, let me draw just what is matched. Right, so So let's suppose that this is I minus j, and this is j minus I here. In this example here that I drew, they both had size 2, but I'm just drawing them now to have size 4. And there is some matching. And potentially there are other edges. So here in y, I'll label these y1 to yt, here z1 to zt. So potentially there are some other edges. I've drawn these in a special way, and we'll see why in fact this has to be the case. So here's an exercise that essentially says that by renumbering the pairs that are matched in N, the squiggly lines here denote the perfect matching N that's guaranteed by assumption of what we're trying to prove. An exercise is to show that since N is the unique matching, the only matching, in A of I, again matching between the symmetric difference between I and J, then we can order the pairs. We can order the pairs yi, zi, so that yi has edges to zj only for j less than I. So you can see that this is how I drew it as well here. So for example, the third node here has an edge to the first node, and the fourth node has an edge to the third node and to the first node. But the second node does not have an edge to the third z or the fourth z. And this exercise is asserting that we can always do this. And this is the key property of uniqueness. This is where we're using uniqueness, that we can, in order to order these in this way. Okay, so this exercise asserts that this little graph on the upper left is essentially what, through reordering, we can have it look like this. And again, what are we trying to prove? We're trying to prove that I can swap all of the y's for all of the z's simultaneously and end up with an independent set. Okay, so just to show you the previous picture, it's saying that I can throw out all of the y's in the matching, add in all of the z's that are in the matching, that would take me from I to j, and end up in an independent set. This is the conclusion that we want. So let's prove it by contradiction and see where we get stuck. So indeed, let's suppose not. So in other words, if j is not an independent set, well, we know something about that. If something is not an independent set, it must contain a minimal non-independent set. That's called a circuit. So it means that there exists some circuit of J. And again, note that it must be that this circuit can't be entirely contained. Can't be entirely contained in the nodes of J that are also in I. That's obvious because I is assumed to be an independent set. So in other words, C has to have some intersection with these nodes here on the right. Again, just because I is an independent set. So that means that C and all the nodes that I wrote on the right here, Z1 to ZT, is not equal to the empty set. So that means that there is a smallest Zi, which is also in C. Perhaps not all of them are in C, but at least one of them is in C. So let's choose the smallest one. So let's choose the smallest index I such that zi is in C. So what do we know? Now let's suppose it is perhaps it's this one. So what that means is, and that means that would make this equal to yi. Well, what this means is that the rest of the circuit is somehow, let me choose yet another color. It means that the rest of the circuit maybe has some other elements from here, and some other elements of, these are elements in I. We're going to ignore those for now, but the other elements that it has on the circuit have to be later in terms of the ordering. In other words, it could perhaps zi plus 2, zi plus 3, zi plus 10. Maybe those are in the circuit, but zi minus 1 is not in the circuit. So in particular, there is no edge between y and something else in the circuit. We cannot have this edge. So let me write that. Let me write that down. Just in our notation, this means that yi to z, this edge does not exist in our bipartite graph for any z that's in the circuit and part of these elements in J, not I. So in other words, for any z that's in the circuit but not in I, and not equal to zi, yi does not have an edge pointing to that. Obviously, yi has an edge to zi. That's the edge in the matching end. So what does that tell us about any such z in the circuit? So this means that z is in the span of I minus yi. I'll just write it again here, for any z in the circuit minus I minus zi. So again, we're getting used to what this bipartite graph is, so I'll just say again, why is this the case? If z were not in the span of this, that would mean that, well, I know that I minus yi is independent because I is independent, so any subset is independent. And if there's an edge between yi and z, it means I can take out yi, put in z, and I'm independent. So if there were an edge, I'm sorry, if z were not in the span, that would mean that I minus yi plus z would be independent. But that would mean that there would be an edge from yi to z. And we just said that by our ordering, by virtue of our ordering and our selection of the index I, there is no such edge. So that means that zi is in the span of I minus y. And that has to be true for any element of C minus I except for zi. So this in turn means that, I'm just rewriting this rather than asserting this for everything individually. Well, this means that C minus I minus zi is a subset of the span of I minus yi. I'm just copying down the previous line. I'm just writing it differently. But this in turn means that the entire circuit minus zi is in the span of I minus yi. This again is a simple conclusion because what had we subtracted? We had subtracted these points over here. All right, we know the circuit lies somewhere here, and these are all the points that are in I but not in J. And since yi is not in this set that I subtracted, then all of these other points are going to be actually members of I minus yi, and therefore we don't have to worry about it. They're certainly in the span because they're actually in the set itself. So the entire circuit minus zi is contained in the span of I minus yi. Now, by virtue of the fact that zi is in the circuit, and the circuit is dependent, we know that anything in the circuit, Zi in particular, has to be in the span of C minus Zi. That's the definition of C being a circuit. I can remove any element and I don't decrease its span. So that means that Zi by monotonicity of span, this also means that Zi is, I guess actually just by inclusion here, Zi is in the span of I minus Yi. There's a lot of notation here, so if you need to pause it for a second, pause the video for a second, just to think about what why this is a contradiction, I think that's useful. But basically, this is a contradiction because this is where we started. So this is a contradiction because by assumption, Yi, Zi, that's one of the edges in our matching. This is in A of I, which is exactly equivalent again to saying that I minus Yi plus Zi is in I. But that contradicts the statement that's saying that Zi is in the span of I minus Yi, and hence I minus Yi plus anything else in its span wouldn't continue to be an independent set. So the contradiction proves this result. Again, this is a very useful corollary. We're going to build on this in the next slide. But again, what it's saying, I think it's useful to look at this picture again. It's saying that if I have a set I and J, and they're the same size, if there is a unique perfect matching, and again recall that in the proof we use this uniqueness in a critical way, then I can do all of the swaps specified by the perfect matching simultaneously, and still end up with an independent set. Okay, let's keep going and show another corollary that is very much in the spirit of this result. Again, M as always is our matroid. I is an independent set. J is some other subset of the ground set. And I is equal to J. And now I'm going to suppose that the rank of I union J is equal to the rank of I. So in other words, this is essentially saying that J is in the span of I. Now, since we have this result that I is equal to J, if there is a unique perfect matching, then we know that J is also independent. This corollary is going to assume that there is such a unique perfect matching, but it's also going to conclude something that's stronger than the previous result. So let's suppose that in our bipartite graph with arcs A of I, suppose that A of I contains a unique perfect matching, we'll call it again N, on the symmetric difference between I and J. Okay, so again, the previous corollary at this point asserts that J is also an independent set. We can just swap all the elements that are in I but not in J with the elements that are J but not in I and have an independent set. Now we're saying something different. Let's let S be some element that's in neither I nor J, such that S augments I. The result of this, the conclusion of this corollary, is that S also augments J. So let's let S be in I and J, such that I plus S again lands you with an independent set now of one larger size. Then that same element also extends I. So again, let me make this note that the previous corollary tells us that J is an independent set. And that's all it tells us. So the difference between the previous corollary and this corollary is this assumption and the fact that I can add something to, if I can add something to I and increase it, then I can add something to J and increase it. And note that without this rank assumption, this wouldn't hold. I'll just leave this as an exercise, that without the assumption that rank of I and J is equal to the rank of I, this result could fail. So make sure that you can see why that is the case, and therefore why we would need that additional assumption. Okay, so this is about extending independent sets. So let's prove it. So what we're going to do is we're going to actually directly use the previous corollary, but on a larger matroid. So let's create a new element and enlarge the ground set. Let's call this T. And therefore look at the matroid M dash, which has ground set E union T. And independent system I dash, where something is an element of I dash if and only if I take T away, if T were in it at all, this is just in I. So in other words, any independent set in I is an independent set in I dash, and if I add, and the new independent sets in I dash are just the old independent sets with this element T appended. Okay, so our picture here is, we start with our familiar picture. This is I. This is E minus I. And J is this set. This is the element S that I'm adding to I. And by assumption, this is what extends I to be a bigger independent set. And let me draw the new element T up top. So this is our picture so far. And we know by assumption of the theorem that, again, there exists a unique matching, not just a perfect matching, but a unique matching between the elements, between the symmetric difference of I and J. Okay, so now let's consider the directed graph on the extended matroid M dash. So let's consider our directed graph on M dash on the independent set I union T. And again, we know by definition of I dash that I union T is an independent set in I dash. So since I plus J is not in I for any J that's in J but not I. Again, how do I know that? Note that this edge says that when you're adding something that's in J and not I, you need to subtract something from I to stay an independent set. That's the only guarantee. And by virtue of the additional assumption that this corollary has that the previous corollary didn't, namely that the rank of I union j is equal to the rank of I, that means anything I add from j to I is not going to enlarge my rank, and therefore I plus j plus little j cannot be an independent set. It would have the same rank as I. So since I plus j is not in I for any j in I, then this means that there is no arc from T to j minus I. So there is an arc like this cannot exist, because if there were such an arc, it would mean that I union T is an independent set, and I could swap T for one of these j's, and I union that j would be an independent set. But that's exactly what doesn't hold by that rank assumption. So there is no arc from T to j minus I. On the other hand, there is an arc from T to S. However, there is an arc from T to S. Again, this is just because if I remove T and add S, I have I plus S, and S was that element which we know, which by assumption says that I plus S is going to be an independent set. And this is by assumption. So now we can apply exactly our previous theorem. Since this edge T to S exists, and there's no other edge from T to j minus S, and since there was originally just a unique perfect matching, there still is a unique perfect matching in this larger graph. In other words, hence N with this new edge TS is a unique perfect matching on the symmetric difference of I and j with these two additional nodes S and T. And so what that means is that I can do all of the swaps in the picture. That would be all swaps specified by these four edges. I can do them simultaneously. So hence, by the previous corollary, it means that J union S is an element of I dash, but J union S doesn't even contain T, so this means that J union S is also an element of I, which is what we wanted to show. So we're going to see for matrix intersection that this is that this result and the previous result are going to be very useful for us.